Okay, so we're back with part two of 522 for October 29th. So before the break, we talked about the factor analysis model. We said that the factor analysis model has an implication for what the covariance matrix will look like, right? So we came up with this equation right here. Now there's a lot of derivation that goes into getting this. It, as we mentioned, it invokes a lot of the assumptions in factor analysis to get to this point. But once we're at this point, we can really start talking about what factor analysis is. So we said the covariance matrix is a function of the loadings. So the loading matrix times the transpose of the loading matrix plus um, the error variance. And we said before the break that what factor analysis does on a technical point of view, what it's really doing, no matter what we say it's doing, this is what it's doing based on the technical details, is it's trying to reproduce the covariance matrix. It's trying to reproduce the covariance matrix. And when we get into looking at structural equation modeling a little bit, we're going to see that this idea of reproducing the covariance matrix is really, really important, because this whole idea of the reproduction of the covariance matrix generalizes to a lot of models, not only factor analysis. You could even fit ANOVA and regression type models into this framework. And some of the best contributors to structural equation modeling have shown how that's possible. So, as we kind of move up the modeling hierarchy and to more complex models, you start to see other models as being special cases. Well, once we get to identities like this, there's a whole bunch of models that could be assumed under this type of framework of the reproduction of the covariance matrix. We compared it a little bit to the regression idea over here. So informally, we kind of saw how this could actually be a special case of that wider framework, but we didn't go into detail into how that actually works. So the question we asked before the break is, if the covariance matrix can be shown to be a function of these loadings, right, of the loading matrix, which is what this is saying, we pointed out that the loading matrix does not contain any observed variables. So we, again, did that comparison to PCA. We said this is not PCA. This can't be PCA, because in PCA, the component scores, right, the component scores were a function of observed variables, right? So when you look in James, calling these things Z, I'm just calling them Y just to relate some of this stuff, but calling them Z, we said these are observed variables. Factor analysis, this doesn't contain observed variables. And at first glance, you start thinking, well, how can it not contain observed variables? Well, this is where the idea of factor analysis comes from, because it's built, the covariance matrix is a function of a latent structure. One latent structure, maybe two, maybe three, maybe four. And all you're going to have are the loadings for that latent structure. Okay, so let me just repeat that for a second. The observed covariance matrix is a function of latent variables. And all you're going to have for those latent variables are the loadings. So what's the big decision that has to be made in factor analysis? I mean, we're at the crux of it here. What's the big decision? The big decision is, what should this contain? What should this contain? Well, it's going to contain loadings, but the question is, for how many factors, right? For how many factors? So if I look at my factor vector, F1, F2, F3, how many factors are going to be in that loading matrix? The factors are unobserved, but how many factors am I going to want to infer on that loading matrix? So let's just put this idea over here, and let's say that we have our vector x, okay, our vector x, which means we have a whole bunch of variables in x. We have x1, x2, x3. What are X1, X2, X3? Well, again, maybe they're verbal, quantitative, and analytical, okay? And again, we can say, well, boy, those aren't really observed, but we'll stop there. We're just gonna assume that they're just observable variables and move on. So we say that the observed variables, right? The observed variables are a function of different loadings. So I'm gonna have F1, maybe F2. These are unobservable factors. So the unobservable factors have loadings that I'm getting from these loading matrices. So maybe I have something like this, 0.70, 0.20. Consistent with our factor analysis model that says X is a function of the loadings by the factor, this is what we're representing right here. The first variable is a function of the loadings by the factors. That's why in this particular equation here, we don't see any observed variables because there are none. All there are loadings. All there are loadings. So the job of factor analysis from a purely technical point of view is to reproduce the covariance matrix, but you're going to have to decide as a user of factor analysis what that loading matrix should contain. And that loading matrix, all you're going to get are a whole bunch of loadings, and you're going to have to make the inference that there's a particular number of factors that are responsible, for lack of a better word, for generating the observed variables. You're going to have to make the decision of how many factors are underlying the observed variables. And the extent to which you can do that and the extent to which your model fits well, you're going to be able to reproduce that covariance matrix. This variable here is unobserved. All you have for it are the loadings. All you have are the loadings. Now you say, well, it's unobserved. Well, it's unobserved, but you're going to infer that it exists based on how much that factor loads onto the different variables, right? And these are observed. All over here are observed variables. So though it's unobserved, although these factors are unobserved, you're going to choose them based on, what's contained in those factors, for lack of a better word. So does X1 load highly on factor 1? Does X2 load highly on factor 1? Et cetera, et cetera, et cetera. So we got our observed as a function of factors, observed as a function of factors, and there's the loadings, which we said has, it can show that the covariance matrix can be written as a function of those loadings. These two equations right here, right, summarize a lot of stuff of what factor analysis is actually doing. So from a substantive point of view, now we move into the substantive, not just the technical. This is the technical stuff of what's going on. You're going to have to decide, do you want one factor? Do you want two factors? Do you want three factors? Do you want four? How many factors subsume the observed variables, right? How many factors, F1, F2, etc., subsume X1, X2, X3? In our previous example, X1, X2, X3 were verbal quant analytic, and then we had IQ down here as a one-factor model. I hope that makes sense as to what factor analysis is actually doing and how it's different from principal components analysis, because in principal components analysis, we never did anything like this. So right away, when you look at like a book that says, well, principal components analysis is the same thing as factor analysis, they're really not the same, because in principal components analysis, we had observed variables over here. In factor analysis, they're unobserved. So how many factors does that matrix right? Does this matrix right here, these are the same, does it contain? Does it contain one factor? Does it contain two? Does it contain three? Does it contain four? How many does it contain? When we were doing principal components analysis, just to draw the analogy back to PCA again, because that comparison is, it's everywhere. And you need to see the differences between the two. What did we do in principal components analysis? Well, in principal components analysis, how many components subsumed the observed variables? Okay. In other words, how many components were we able to get from the observed variables? Were you able to get as many components as there were observed variables? That's what components analysis did. Components analysis was very, for lack of a better word, atheoretical. It didn't ask you to come up with like latent factors or to kind of like try to think of what is this factor, what is this factor, etc. All it did was transpose the information, transform it, performed an orthogonal transformation on the data. And if you entered the situation with three variables, it generated three components. In that sense, it was kind of simple, right? It's like three observed variables, three components. Now, after that, you could choose how many components you wanted to keep, right? You could choose how many components you want to keep, but principal components analysis was just doing that transformation. Factor analysis is different, okay? Factor analysis is different. How is it different? How is factor analysis different? Well, first and foremost, not only are these unobserved ideas, you can say that in components analysis, you really couldn't observe the component, so that'd be fair to compare the two and say, you know what? Components analysis is kind of similar because we didn't know what the component was, just like we don't know what the factor is. That's fair. But here's where things are going to start to be a lot different between components analysis and factor analysis. In components analysis, let me just put those three variables down here for a second again. In components analysis, if I enter the components analysis with those three variables, I'm going to get three components. I'm going to get three components. So I'm going to get C1, C2, and C3. Those are going to have loadings on them over here, right? So this is in 0.40, 0.70, etc. Now, these components, you may say, boy, this looks a lot like what we're doing here, but it's not quite the same because these components are a result of the transformation of the data, so that if I get three components, which I have to get because I have three observed variables, but I choose to keep the first component. Okay, so I choose to keep the first component and I say, you know what, I'm just going to use the first component. These two components here, they just remain the same. In other words, I'm going to take this component, I'm going to say, you know what, there's a one component structure to this data. This component explains 80%, let's say, I'm making it up, 80% of the variance in the variables. That's all we're doing. We're just keeping that component. The PCA has done its job and it's done the transformation. It's an arithmetical procedure that was done on your variables in the form of an orthogonal transformation, period. That's all it's done. And it's over. It's over. In PCA, you're done. You do the eigenanalysis, because that's what's actually, one way to get the components is the eigenanalysis or the singular value decomposition, and you do that and you get the components. From there, you can choose how many you wish to keep. As I'm doing here, I'm saying I'm going to take the first component, I'm going to discard these, but it's over. Factor analysis is not the same, and here's how it's different. First of all, this isn't a component, this is a factor. So factor 1, factor 2, factor 3. Now, look how it's different. Well, I'm just going to delete this because usually you're not going to be able to get a third factor because factor analysis is going to focus on the commonality between variables and not simply the variance in the variables. So right away, in most cases of factor analysis, you're not going to be able to generate those three factors in the first place because it's focusing on the commonality of the variables, x1, x2, x3. So it's focusing on the commonality, which means it's not simply doing a transformation as we saw in the PCA. So first of all, we'll get rid of this and let's just say we have the two factors. Unobserved, unobserved, I'm going to look at these particular loadings. These particular loadings we know are from this matrix here. This matrix here, to refer back to what we're doing here, this matrix here in this sense contains two columns of loadings. There's one column, there's another column. So this particular matrix, 0.90, and I'm going to put, say, 0.30, yeah, 0.30, and I'm going to put like 0.10, 0.10. There's one particular column of loadings. Then I'm going to have the other column, 0.70, 0.60, and 0.40. There's another column of loadings. In this particular case, this loading matrix has two loadings, two columns of loadings. Therefore, it's suggesting a two-factor solution. And again, you say, well, that seems a lot like PCA, but it's not the same as PCA, and here's why. If you look at these two columns and you decide that you are going to keep the first factor, okay, you're going to keep the first factor. Why? How are you going to base that? Well, maybe it has a structure that you can make sense of that goes along with the observed variables. So your decision to keep the first factor should be based primarily on substantive theory, not simply a numerical figure, okay? So you're going to say, well, I'm going to keep the first factor. Here's how factor analysis is different. If you redo the model, if you redo this model and you choose only a single factor, you ask factor analysis, select only a single factor. Don't select two. In this case, you're selecting two. If you redid the model and selected only a single factor, therefore this one doesn't exist, what's going to happen to all these loadings? These loadings are going to change. Okay, these loadings are going to change. Let me just repeat that. Is that, here you say, hey, I've got a one-factor solution here. I've got, this is the factor I want to keep. I can make substantive sense out of it. Maybe these loadings are actually a little bit higher. Let's put 8.0. Let's put this like a 0.90. I can really make sense of this structure, let's say. So you want to keep factor one. Well, it's not quite the simple thing as in PCA. In PCA, you can keep the component one, and like I said, it's over. While the procedure says I selected two more components, I just want the first component because it explains 80%. Factor analysis, you keep the first factor. This one still exists in the solution. So then you say, well, let me get rid of this one. Let me run the factor analysis so that I just select the first factor. If you do that, these loadings will change. And when you think about that, you think that sounds a lot like what? That sounds like a lot like regression analysis, right? It sounds like a lot like regression analysis, where in regression, if you have x1, but you input x2, what happens to the b coefficient for x1? It changes. Context, right? Context. The context issue, just make sure that's clear, right? So you put in x2, this changes, which again, forms like the basis for like those mediational models and all that. But the weights are going to change. The weights are going to change. That's what happens in factor analysis too. Why does it happen in factor analysis? It happens in factor analysis because when we look back as to what factor analysis actually is, right? What is factor analysis? It's a regression equation. It's a regression equation. It's a regression equation, only it's different from regression analysis, because in regression analysis, these are observed variables, right? In regression analysis, there isn't a latent, these aren't latent variables, they're observed variables. So in regression analysis, you're getting regression coefficients for observed variables. In factor analysis, you're doing a regression equation as well, only you're doing it for unobserved variables. Okay? But that's why those weights are going to change. That's why the weights are going to change, because you're doing something very, very similar to what is done in regression. They're not the same. They're not identical, because how can they be identical if one has unobserved variables and one has observed variables? So they're definitely different, but you can appreciate why the weights are going to change. Why the weights are going to change. Now, you say, well, okay, that's fine. That's a technical issue. Who cares? Well, it's going to make a big difference in terms of your substantive theory as well. Because if those weights are going to change based on how many factors you run the factor analysis on, then the question is, what's the correct solution? What is the correct structure for our loading matrix? Is it a 2-factor solution? Is it a 1-factor solution? If you run the factor analysis with 2 factors, right? If you run the factor analysis with 2 factors, but keep 1 factor, that's different than running the factor analysis with only a single factor solution, where this is not even produced. Okay, where this one's not even produced. Now you liken that to regression analysis. Again, the parallel is very, very meaningful here. It's very useful because they are both regression equations. If you look in regression, you understand it perfectly because we've stressed this so much. I mean, we stress this to ad nauseum as to why, how this works. If you have y here and you go x1 predicts y, you get a b. If you do x2 predicts y, along with x1, this changes. So the correct interpretation of the b for x1 was what? Well, for a 1 unit increase in x1, we expect on average such and such change in y given the inclusion of x2, given the model of x2, holding x2 constant, that type of thing, right? You had to mention x2. Well, look in the factor analysis model. It's very similar. Because if you run it with if you choose a 1-factor solution, but you initially ran 2, right? You asked the computer to select 2 factors. You said, select me 2 factors, but you liked factor 1, then technically speaking, you have to report that you ran the 2-factor solution. You didn't run a 1-factor solution, you ran a 2-factor solution. And that is very similar to saying, I like x1 as a predictor, but I obtained, that preference for x1 in the context of x2. I did not just like x1 with this disappearing, with this like not even entered into the model. That's how those two are the same. You have to mention the idea that you extracted, right? You asked the program, you asked the algorithm to extract 2 factors from which you decided on 1 factor. And why is that? Because the weights will change. The weights will change. Okay, so that's really, really important. We're going to unpack that a little bit further. I just want to mention what's going on here. This whole identity here of the observed variables being a function of the factors, the reason for that is over here if you wanted to work through the argument as to why that works. And it involves taking expectations and such, but this is what we end up with. So just to make that long story short, this is what we're getting over here, which is what we had up there. That's what all that is. It's just showing how does the factor analysis model go from our factor analysis equation to this? Well, it's up here. And there's more to that derivation, but a brief summary is up here if you want to look at it. So let's get back to this issue of why this is so important, right? Well, this is important, as we mentioned, because we're trying to reproduce or regenerate the covariance matrix. So we said that the actual job of the factor analysis is to justify the reproduction of the covariance matrix based on meaningful substantive solutions. So when we're saying what's going to go into here, is it going to be a 1-factor solution? Is it going to be a 2? Is it going to be a 3? The decision criteria that's going to go into there is that it should be a meaningful or substantively productive solution. And that's where factor analysis gets a little bit of its kind of subjectivity, because you're going to actually have to decide how many factors are going to be part of the factor analysis, not based on only a quantitative criteria, but based on whether the factor actually makes sense. So that's what I'm saying here. The trick in factor analysis is to specify a matrix of loadings that is best suited in reproducing the covariance matrix. Should it contain a single factor? Should it contain 2, 3? And that's a decision you have to make. But the important point to recognize as well is that the decision you're making has to be noted in the context of how many factors you are computing, for the reasons we just mentioned, because those loadings will change depending on how many factors you extract. The loadings can actually change so much that you find a 1-factor solution when extracting 2, but that things don't quite work out or change quite a bit if you only extract the 1 factor. So again, it becomes tricky in terms of understanding. If somebody says to you, somebody at a research conference says, I did a factor analysis, I found a 2-factor solution, right? They say, I just found a 2-factor solution. That's the start of the discussion, right? Because the next question is, well, how many did you extract? And if the presenter says, well, I extracted 4, but I chose to keep 2, right? I extracted 4, but I chose to keep 2. That's entirely different than running a factor analysis to just get 2 factors. The actual solution that the person got was a 2-factor solution in the midst of extracting 4. And then you have to ask, well, why did you extract 4 to begin with? Okay, because that context of how many factors you extracted matters. Okay, so we're starting to look at some of the issues with factor analysis and why it's different than PCA, because remember, just to reiterate, PCA, that never happened. PCA, if these are components, right, C1, C2, C3, C4, if you took out 4 components, the procedure is going to take out 4 components. It's not hiding anything. It's not saying how many components you want to take out. It's taking out 4 components. It's doing it. Guaranteed it's doing it. Even if you tell the program, you tell SPSS or R or SAS or whatever, you say, I just want 2 components. It's computing 4, guarantee it, even if it's showing you 2. Factor analysis isn't quite the same. In components analysis, you're going to say, I'm going to keep these 2 components. These 2 components don't change depending on whether you extracted 3 and 4. They are what they are. In that sense, the PCA solution, I mean, for lack of a better word, again, verbal labels are tough to describe these things, but you say, well, it's kind of stable. And by stable, I don't mean that if you repeat on new data, you're going to find the exact same solution. By stable, I just mean that whether you compute 4, you compute 3, you extract 3 or extract 4, the component values here don't change. They stay the same. And that is entirely different in the factor analysis model. Okay. So any similarities between factor analysis and principal components analysis, the similarities are going to be there, and you're going to look at books where they say, they're pretty much the same. Well, oftentimes they kind of come up with the same structures. That's why when people say PCA and factor analysis are the same, they aren't the same, but they often suggest a similar structure, but not always. And they do different things. So we have to be aware of the differences. What we're focusing on here is how they are different. Because if you understand why they're different, then at least when you see that they're producing similar output for a problem, you'll still know that they could produce other things, and in some cases they will. And it'll also help you understand error messages in software when you get them, right? You can get an error message when you try a factor analysis that says, I can't compute 4 factors. Well, I can compute 4 components, but I can't compute 4 factors, and you'll know the differences between the 2. or at minimum, you'll know there's differences. You'll know you'll need to dig further to see why isn't the computer, computing what I thought it could compute. So we've talked about one issue there. Let's put this into words a little bit. And this is the indeterminacy of and the non-uniqueness of solutions. Okay, so we're going to talk about this critique and unpack it a little bit more, kind of related to what we just talked about. This idea is related to both the idea that we said, but that the determination of the number of factors depends on how many you extract, how many you compute. That is absolutely true. But there's also another issue with factor analysis, is that the estimation of that loading matrix, okay, the estimation of that loading matrix, we can say it provides a unique solution, but only up to an orthogonal matrix. Okay, so up here we're saying that the loadings are not unique. Well, that's true. The loadings are not unique. But another way of saying that is it produces a unique solution, but only up to an orthogonal matrix. Which means what? Which means you can transform those loadings. You can transform those loadings and still just as well produce this. Okay? You can transform the loadings in here and still produce this. So I'm just going to put, here are the original loadings. Here are the transformed loadings. Original, transformed by a way we're going to talk about. How do they transform, right? You're maybe wondering, well, how are they going to transform? We're going to talk about how they're transformed. But the original loadings and the transformed loadings can both equally generate this. They can both equally regenerate that covariance matrix. So the fact that we can issue a transformation on the loadings and it still produces this will raise the question as to, should we go with these loadings? Or should we go with the transformed loadings? That's what we mean here by an orthogonal matrix. And what we're getting at in this idea here is the idea of rotation. The idea of rotating the factor solution, which will still produce the original covariance matrix. So if we can transform the loadings, and again, you don't even have to think of it in terms of a rotation. It will be a rotation. But you can just think of it even like more conceptually. By the way, when we say conceptual explanations, we're not meaning like a watered down explanation. The conceptual explanation is often deeper than what the math is representing, because the math can only go so far, right? You look at the math and you say, well, what is this doing? Well, it's doing this, right? And you think of somebody pointing to the math, it's doing this. Well, this is a representation for something, right? Math identities and objects come from somewhere, and they come from people wanting to represent ideas. So again, when we say conceptually, we're not meaning watered down. In some cases, we're actually meaning here's the deeper interpretation of what this kind of notational stuff is representing. And what I was mentioning there is, if you can perform some transformation on this and it still reproduces this, then you're going to be left with a problem as to which ones to choose. And the nature of the transformation will be rotation. But again, think of it just more generally as, you're going to transform something. So, there's a square, and imagine I'm using the square to reproduce this. Well, if I told you that I could transform this into this, and it still just as well reproduces this, it's not that it reproduces it more poorly, it reproduces it just as well. Then the question is, which shape you're going to go with, this one or this one? And that's going to be the problem. So regardless of the solution obtained in the estimation process, we are able to quite freely rotate the factor solution, rotate, transformation, yet still provide the same reproduction of the covariance matrix as with the original solution. So Muleik, who wrote like the Bible on factor analysis in 1972, it's like 300 pages, and you can study it for a year and it still won't be done with it. That's that thorough. Muleik writes, factor analysis, at least in the traditional sense, is concerned with the problem of analyzing a variable into components, okay, into factors. From a strictly mathematical point of view, from a technical point of view, look at this. there are an infinite number of potential sets of components which might be determined for the given set of variables. Okay. Because of this mathematical ambiguity, the history of factor analysis has been filled with controversy over what are the appropriate components into which to analyze a set of variables. And the controversies are, they're not over. Okay, so we're entering the complexities of factor analysis, the main points that you need to understand so that when you do factor analysis, when you hear somebody say, I did a factor analysis, these issues are all like underlying the procedure. And when Mulayek says from a mathematical point of view, there are an infinite number of potential sets of components which might be determined for the given set of variables, what is Mulayek talking about? X1, X2, X3, F1, F2. So I'm just going to go with that two-factor solution, 0.7, 0.3, I forget what those loadings were, it doesn't matter, 0.9, 0.1, 0.2. What this paragraph says, and this idea of an infinite number of potential sets of components, is that you can transform these weights. You can transform these weights many, many different ways. Infinite number of different potential sets of components that will reproduce this. This is what this is saying. So you can issue rotations on this, transformation. Rotation is a type of transformation that will still reproduce this. Okay? Problem number 2. What was problem number 1? Problem number 1 was, well, depending on how many factors you actually extract, you're going to get different loadings. So remember, that context exists, right? If you extract a 2-factor solution, the loadings may look different than if you extract a 3-factor or 4-factor and that you select a subset of the factors. So there's complications there. But here's one of the biggest complications is that you can subject those factors, right, those factor loadings, to a rotation, to a transformation, and you can just as well reproduce this. The question is going to become then, if you rotate these factors, and you can just as well reproduce this as the original solution, then what's the correct solution? Right? What's the correct solution? So let me just repeat that. If you rotate the solution that you obtain in factor analysis, and you're just as well able to reproduce this, okay, you're able to, the fit is going to be just as well, and there's an infinite number of possible sets of components, then among that infinite number of possible sets of components, you're going to have to somehow have some criteria for making a decision on what the right component or factor loading matrix is. Right? Does it contain 1 factor? Does it contain 2? Does it mean we extract 5 but keep 1? Does it mean we extract 6 factors and keep 2? That was problem number 1. What I just talked about was problem number 1. Now problem number 2. If I rotate this solution and the loadings change, which is the correct solution? Is it the original solution? Is it the rotated solution? Is it the rotated solution by using a different method of rotation? Is it the rotated solution using yet another different method of rotation? Because all of these things will still fit the factor analysis model. So in other words, there's an ambiguity. There's a mathematical ambiguity. And if there's a mathematical ambiguity, then there is a substantive ambiguity. Ambiguity, right? The mathematical ambiguity suggests there's going to be a substantive ambiguity unless we've got some way of making sense out of this to get us out of this mess. I mean, look, if you have an infinite number of solutions, you're going to have some way of choosing which solution you want. This is the problem. You're going to have some way of choosing the solution you want out of the infinite number of possible sets of components. So the mathematical ambiguity is giving rise to a substantive ambiguity, and you're going to need a way out of it. Over here, there's the unpacking of the argument as to why the factor solution is only unique up to an orthogonal matrix, which is what we just said. And you can look at this argument here. We'll get to the bulk of it, but there's our orthogonal matrix here. That's a transformation matrix, which we know we can write the matrix this way based on matrix algebra, based on things like in Fox, where you have the identity matrix. If I insert this matrix product here, T times the transpose of T, into my original factor analysis solution. Okay, so I'm just inserting it in there. So I've got my original factor model. I'm inserting T by T prime, T transpose, just putting it in there. Well, look how we can write this model. T times T transpose is equal to I over here. So we can write it this way. We can write it this way. But when we work with this expression a little bit more, we realize that this here can be written this way. Okay, this here can be written this way, where I've just put brackets around those two. So we can consider our original matrix of loadings subject to the transformation T to be equal to the loading matrix times T, and the vector of factors to be equal to T times T prime. That's exactly what we wrote here. So the implication of that problem is that through the orthogonal transformation, right, through this orthogonal transformation using T, we are able to define a new loading matrix times T, and a new factor vector. Okay, and a new factor vector. This is the idea of the rotation, that if you can make the transformation and you'll have a new loading matrix and a new factor vector. So when you look at this a little bit more, the question is, does this new definition of our loading matrix and factor vector change things in terms of the model? Well, when you work through the expectations of this, which you need to figure out what the mean of the factors are, etc., we see that the expectation of the transformed factor is identical to that of the untransformed factor, which means the original factor vector and the transformed factor vector have the same mean. In other words, what we're saying is you can issue the transformation and you're going to have the same mean. The expectation is going to come out to be 0. What this means in the bigger picture is that you're going to have a consistency. It's not going to change things. In other words, you can issue the transformation, but it's not going to change things. Okay? It's not going to change things. Similarly, we have to ask whether the transformation, right, changes the expectation of the covariance matrix. Well, when we input that transformation, the covariance term becomes this. There's the covariance of F right here. Since T is an orthogonal matrix, and by definition this holds, this means that that remains I. So the transformation of F by the orthogonal matrix does not alter the expectation for the covariance matrix of F. What this means is the original covariance matrix and the transformed covariance matrix have expectations equal to the identity matrix. So big picture as to what this means is whether we use this or whether we use this, right? There's that, remember that's the transformation I put in there. We've looked at some of the implications of that transformation up here. That's what that's doing. Whether you use this or whether you use this, we are able to reproduce the same covariance matrix. Okay, so whether you use this original factor model, this is what we first surveyed, or you use this, where you're putting in T, you're putting in that transformation, you're able to reproduce the same covariance matrix. So what's the big deal? Both the original loadings and the transform loadings generate the same covariance matrix. So the original and the transform, whether you choose the original loading matrix or the transform, both can reproduce this just as well. Right? Both can reproduce the covariance matrix. What we've just talked about is this idea right here. This is what Mulaic is talking about, and why there's controversies surrounding factor analysis, and why you just have to know what it's producing. Doesn't mean it's wrong, doesn't mean it's bad, doesn't mean it's not valid. You just have to be aware that this thing could produce a whole bunch of different solutions, yet you can still get the same fit on the covariance matrix. And that's why we say there's mathematical ambiguity, but it leads to the scientific ambiguity. Why there's unclarity, a lack of clarity as to the true nature of the factors, because there is not a true nature to the factors, because there are so many different options producing the loading matrix. So here's the big picture, is which loadings are the correct loadings, the ones originally derived, or the ones derived through an orthogonal rotation? What's the implication from this from a scientific point of view? Again, remember, you're using all of this stuff, right? All of these statistics, there's a bunch of technical details that we're looking at, but you're trying to like use this for a scientific purpose. And to be completely honest with you, the technical details, you can work through those and you can say, okay, well, this kind of makes sense and stuff like that. That's actually not the hardest part. The hardest part is actually using this in a scientific sense and being able to defend it. So if you're using factor analysis and you're aware of all of these issues, that's going to be pretty hard for you to defend if you actually had to unpack these issues and say it supports your factor model. Now, maybe you won't have to, but you still need to be aware of the issues, and it needs to feel right with you too. You need to feel that you're producing something of scientific value. If I told you there's a billion different ways of producing something, and I'm going to choose one of those ways, that's hardly kind of scientific, right? Because then someone's going to say, why are you choosing that way? Well, it was my preferred way, right? There's a billion different ways, and I chose this way. You're going to have a reason for why you chose that particular way, and that should be defended. So let me just look at this in an analogy way, is to kind of like the wrong way to interpret factor analysis, right? So many times with statistics and methodology, if you look at the wrong ways and you peel away the wrong ways, you say, well, that's wrong, that's wrong, that's wrong, maybe you'll be left with what it could actually do, which sometimes is quite limiting, right? But you peel away all the wrong layers and then you say, okay, so I guess it can just do this. So then any of those verbal labels, right? Any of the verbal labels, which we've talked about a little bit already, you associate verbal labels with it and you say, wow, factor analysis can do this. It can do this, it can do this. It's like, no, it can't, no, it can't, no, it can't. All it can do is this. And that's why it's important when you're looking at some of the theory, so you know what it does and what it doesn't. And they tell you, well, this car is going to do this and that and this. And it's like, no, it won't. It can only do this and it'll break after 50,000 miles, right? You have to know the truth of what it's actually doing. So let's compare this to like the Jurassic Park thing, right? The archaeological dig. So there's the desert at the beginning of the movie. They're in the desert and they are doing an archaeological dig. So there's the archaeologist and the dinosaur is underground, and there's the dinosaur there. Maybe it has some wings, I'm not sure, but the dinosaur is underground. There's one archaeologist and another one, and they don't quite have the technology, so they are, there's a shovel and they're digging. Well, they're digging and they're finding a structure. They're finding a structure. So they say, we found a structure underground. They identify the structure as a dinosaur. So they say, we found a dinosaur. Well, that is entirely different than what this is about, right? Let's compare it to these two people. Instead of looking for a dinosaur, they're looking for factors. Well, everything we've talked about so far says that if I were to draw the analogy, it would be like this. Hey, we found a dinosaur, but this dinosaur, the structure of this dinosaur is contingent upon us finding, that is not very good, but anyways, that's actually the face over here. Finding another dinosaur. Factor 1 and factor 2. Archaeological digs don't do that because they can just deal with concrete reality. They can say, there's the dinosaur. We don't say, how many other dinosaurs did you find so I can make sense of the first dinosaur? That would be, just, we wouldn't say that. But the factor analysis has to do that. And not only that, not only discuss how many other factors were obtained with the solution, they have to accept the fact that different rotations, right? Different rotations of the structure are going to produce the same covariance matrix. In other words, different transformations of the structure are able to produce the same reproduction of the covariance matrix. So the question then becomes, what are the correct loadings? What's the correct, almost like if drawing the analogy to the dinosaur, what's the correct configuration of the dinosaur? Again, that doesn't exist in archaeological digs because they don't have to do that. But you see that so many of the things in factor analysis are contingent on those things. So how do you choose the correct loadings? You can run rotation after rotation after rotation. You can select 5 factors, you can keep 2, you can select 2 factors, you can keep 1, all of that stuff. But science necessitates you to have a solution. We know that the COVID virus works because we ran it in the experiment, or the COVID vaccine, and the people are not getting the disease, so we know it works. So you have to ask the question, how am I going to know my factor analysis works? But it cannot simply be by reproduction of the covariance matrix. So what's the answer? What's the only answer that can happen? What's the only answer that it could be? The answer has to come from a subjective consideration regarding which loadings make the most sense to the researcher. So out of that infinite number of solutions, that's why I put up here, you're going to select, I put it somewhere up there, we're going to have an infinite number, I'll redraw it here. You have an infinite number of solutions. These are like an infinite number all the way to infinity. You're going to select this solution based on subjective considerations and based on it making the most sense to you as a researcher in terms of reproducing the covariance matrix. So you cannot say things like this. You cannot say, well, I've chosen this solution because it reproduces the covariance matrix. That would not be correct. In regression, you can say that. You can say, you know what, this regression model right here, AX1 plus AX2, I like that model. It gives me a high R squared. Right? You can say I'm choosing that model because it gives me a higher R squared. Now, we've talked about in regression, as you include more predictors, R squared is going to increase. So you need to balance that out a little bit. Maybe use an adjusted R squared and an AIC or something like that. But in regression, you're able to justify the model you're selecting based on the extent to which it fits over here. A little bit different in this case because all those rotations, all those transformations are going to still regenerate this. So it's almost like, if you were to think of it in terms of the analogy so far, it's almost like you're still getting a good fit to the covariance matrix. You're still able to reproduce the covariance matrix. So the decision of which solution you're going to select has to come from other means, and that's going to come from subjective consideration. Which structure makes the most sense to you as a researcher? And there's why factor analysis is subject to criticism, because science shouldn't be about which one makes the most sense. We think there's the critic, I'm the critic talking. It should be based on, firm criteria. Well, we'll talk about next time why that criticism is a little bit overdrawn. People make too big of a deal about that, because really we do similar things in regression and other models. but you have to be aware of these caveats. So next time, we're going to look at some examples that come from a little bit from Mayer, a little bit from the Stevens book as well. We're going to look at the idea where you're going to select a solution based on what makes the most sense. And we're going to talk about how to select that solution. And we're also going to talk about how to potentially name these particular factors, if you want to name them or if your theory demands that you name them. Last point to leave off with today is that the factor analysis model definitely does not tell you what these are. Okay, so the factor analysis model will not tell you what factor 1 and factor 2 are. In other words, you can give them completely ridiculous names, yet it still regenerates the covariance matrix. So there's another problem as well, that from a substantive point of view, even naming the factors, there's no justification for the name. So when someone says, I found an IQ factor, they have not found evidence for there being an IQ factor, right? They've not found evidence for there being an IQ factor. What they found was evidence for a factor of which they decided to name IQ. Okay, so there's differences. We got to unpack that a little bit more as well. So I'm going to just post some of these, just a few more of these technical notes, and then we'll finish this off next week and fully finish off the unpacking of the, we're almost there, and look at some examples from Stevens of factor analysis and talk about communalities a little bit. And then from there, we're gonna get into the path analysis and structured equation modeling. You can see where the path analysis and structured equation modeling is going to build directly off of these ideas. Because in structured equation modeling, you're going to have a latent variable here. It's going to be indicated by observed variables here, right? So look, there's your analytical, verbal, and quantitative. There's your IQ. There's your factor analysis. What's the difference between this and structured equation modeling? Look what structured equation modeling does. IQ predicts GPA, and GPA is going to have a factor structure. That's SEM. In a nutshell, that's it. SEM is a regression here and factor solutions over here, and then you can make it as complex as you want. So we'll talk more about that next week. Okay, so that's it for this week. We'll see you next week.